Martina Lanini, who is from Rome and will be speaking to us about singularities of Schubert varieties within a right cell. Just to remind people, we're doing a 25-minute plus 5-minute break plus 25-minute presentation for the long talks. So I'll mention maybe at 23 minutes in that we're shortly coming up to a break, just to remind everyone. Okay, thank you very much.
Thank you, Kevin. Thank you to the organizers. I'm very excited about speaking at this conference. I was very excited about this twin conference. So anyway, as Andrea said, it's it's a situation in which we are thinking about all these distances, how to anyways, let's see how it goes. I'm very excited. So what I'm going to talk about today is some recent work, and so collaboration with Peter McNamara. And so I decided, so what I'm going to do is first to tell you what the key result is, which is going, as you can see it here, to sound extremely technical. Like, okay, it's a good strategy. And then still, I'm going to try to convince you that even if it sounds like, well, maybe it's a cute result about Schubert varieties, but in fact, it has a lot of interesting applications in geometric representation theory. Of course, that sense is not that surprising because we know that singularities of Schubert varieties are related in many, many ways to representation theory. So what I'm going to do is first going through this key result with you, and then telling you what the moral of it is, and then give you three possible applications of this result, and then focus on one of them for the rest of the talk. All right. So, okay, so maybe before going through it, let me first tell you what morally says. So really what this key result is about, of course, the singularities of Schubert varieties, that is telling us that whatever behavior of singularity of a type A Schubert variety you have, well, this can happen within a right cell, Kazhdan-Lusztig right cell. Okay, what does this mean within? So let me first go through the result. Then, so if you don't remember or you don't know what a Kazhdan-Lusztig right cell is, I'm going to give you the definition at least in type A. Okay. So the starting point are two permutations, Y and W, so in Sn. And then, we are, so in the type A flag variety, so just the variety of complete flags in Cn, so complex. And so we take the Schubert variety corresponding to W, and now we assume that it is singular Y, meaning, the flag corresponding to this other permutation. And so now what we claim is that there exists some bigger, so some capital N, which is at least little n, and two permutations in this bigger Sn, such that, again, I do the same. So I take the Schubert variety, this time corresponding to W bar. It's a sub-variety of the variety of complete flags in C capital N. And then it's again singular, Y bar. And then it's the same singularity, but it's sort of sloppy, but that's, we are going to see an example, and I'm going to tell you what I mean by this. And then, well, this would be nothing somehow if you just ask for one. But then these two permutations, the new permutations, are in a nice combinatorial relative position. Okay, so they both belong to the same Kazhdan-Lusztig cell. So we'll see what it is. Just keep in mind, so you have your symmetric group, a cell, so it decomposes as a disjoint union of right cells. And so it's particularly nice if these two permutations are in the same one. So let me just keep it very vague. So let me start properly. So as I promised, I'm going to give you some motivation. So why do we get interested in this? Or maybe I should be here, otherwise you only see my hair. So why do we get interested in this sort of question? Okay. So I start by the motivation we really had, which was a question about reducibility of associated. Can you read? I should write better. Okay. Of associated varieties of highest weight modules well, irreducible for SLN. Okay, so the Lie algebra is SLN. And that was, in fact, is a question from the 80s due to Borov, Brzezinski, and Joseph. It was around 85. So this publication, so Borov, Brzezinski was 84, Joseph 85. So that's the, let me just mention, that's the application I'm going to focus on, okay, from the next page on. So, but there are at least another two. So there are another two applications I want to mention, which are, so one is more, so if the first one was more geometric in nature, the second one is more combinatorial in nature, which is the so-called 0-1 conjecture for, again, type A Kazhdan-Lusztig polynomials. So what this was about, so was, let me say, originating by, again, a question or an observation maybe of Lascaux, Schutzenberger, again from the 80s, 81. So they were studying Grassmannian permutations, and they noticed that, so the highest possible degree term of a Kazhdan-Lusztig polynomial. So we know Kazhdan-Lusztig polynomials are Poincare polynomials for intersection homology complexes. So that means they have a bound on their degree. And so this highest possible term would have always a coefficient either 1 or 0. Okay, so they were like wondering whether for type A was always the case. So, and then in 2003, there were a counterexample, in 2003 by McLaren and Warrington. Well, in fact, they were dealing with two conjectures. So the first one was this 0-1 conjecture I told you about. And then there was a weaker one, which is, okay, maybe it's too strong to hope it's that every Kazhdan-Lusztig polynomial would have this property. Well, then let's hope that the two permutations which index the Kazhdan-Lusztig polynomial lie in the same left cell. Okay. So for the strong form of the conjecture, McLaren and Warrington found a combinatorial way of constructing a counterexample, while for the weaker one, they needed computer help. And so somehow from this key result they stated, you can just deduce the let's say the weaker form of the conjecture from the, you can deduce the failure of the weaker form of the conjecture from the failure of the stronger form. So that's one thing. And then the third application I like to mention, it's more representation theoretic in nature. So it's about a comparison of bases of irreducible representations, let me say special modules for the Hecke algebra of Sn. Okay. And so here I'm not going to be able to spend much time on it. I'm happy if you ask questions about it, or we can have a chat during lunch or whatever. So the vague idea is that, so via the theory of cellular algebras, you get a basis for spec modules by considering Kazhdan-Lusztig basis. And so now you have, for every prime P, you have a P analog of a Kazhdan-Lusztig basis. And in type A, thanks to result of Targe-Jensen, you can show that also, so you can in the same way construct basis for spec modules, but this time using the P analog of Kazhdan-Lusztig basis. And so one wonders whether they're the same or not, and somehow the key result allows you to show that this, that there exist infinitely many examples in which these bases are different. And let me be very vague, or maybe just let me mention this because I think it's cute. It's cool, actually, not only cute. It is related to the torsion explosion phenomenon, if you know what I'm talking about. So the fact that there are infinitely many examples to the fact that these bases are different is related to appearance of torsions in ICs. Okay, great. So now, as I said, I'm going to spend at least the rest of this half talk about the motivation A. So I fixed the usual data. So I didn't want to spend too much time on it. So I have written this already. So we have G as a semi-simple algebraic group, and then we fix a maximal torus in G. So this allows us to define the Wald group, okay, W. Then in between G and T, we have a Borel, B. And so we look at this homogeneous space, which is a flag variety. And then under the left action of B, we write the flag variety as a disjoint union of B orbits. Each one of them is an affine space, and that's a Schubert cell. Now the Schubert variety is the closure of one of these cells, or maybe the only thing I want you to mention is that, and they're all, so these orbits are indexed by the elements of the Wald group. And so our Schubert varieties are also indexed by elements of the Wald group, and there are complex projective varieties in general singular. And as I said, we are interested in the singularities of these guys. Maybe I can also mention that, so they're equisingular along B orbits. So each one of these, the closure is a disjoint union of other B orbits indexed by permutations, which are less or equal to, for example, W in this case, in the Brucha order. And the Schubert variety is equisingular along this orbit. Okay, so whenever I say, for example, as you said in the statement of this key result, I was talking about a Y in XW, so singularity Y is sort of an abuse of notation for Y, B, B. Okay, so we have Y to the left of the element of the Wald group, and then I look at the corresponding point. All right, now I can look at the tangent spaces. So I have the Lie algebras, G, B, and T. And I get as usual root system, which I denote by R, and positive roots are R plus. And rho is the Wald vector. Okay, so it's half the sum of the positive roots. So now I want to introduce some notation for a simple highest weight module for the Lie algebra. And highest weight, well, U, G, or module or G representation. So this is a simple highest weight minus W rho minus rho. Right? So if you want is the dot action, so is WW0 dot 0. Okay. Dot rho. Yeah. Okay. So anyway, I have this simple highest weight module. So I'm not, of course, restricting to only dominant weights. Otherwise, you'll see it's not an interesting case, and that's why we are variating W and W. Okay, so what I was mentioning before is this application to associated varieties. So let me recall for you what this is, or tell you what this is. It might be a bit sloppy because I thought if you know already what it is, you relax. And otherwise, I hope you get a flavor of what it is. So the associate variety is going to be denoted by VLW. Okay. So this is a variety of G dual. Okay. Now let me tell you how. And so the question was about reducibility. So is that irreducible? Okay. That's the question we would like to address. Okay, so how do you define this? So we have our LW. So LW is in particular a finely generated module over the enveloping algebra of G. Okay, so keep this in mind. Now what happens is that it admits, so that's a fact, it admits a filtration which is compatible with the PBW filtration on the enveloping algebra G. Okay. Well, compatible in which way? Well, I can take the associated gradient of LW, And now this is a module over the associated gradient of UG, but this is a symmetric algebra, okay, of G. And this is finally generated now, right? Because we said it was a finally generated UG module. So, well, I don't know if you can read. Yeah, maybe, I hope. Otherwise, you stop me or you raise your hand. Okay, so it's a finally generated SG module. Well, but SG is nothing but, well, I can identify it with regular functions on G star. So meaning that I have a finally generated module on CG star. And so it is really a coherent sheaf on G star. Okay. So I get a coherent sheaf on G star. And so what I do now is I look at the support of this sheaf, and that's the associated variety. So now VLW is the support of such a sheaf. Okay. So we have a variety there, and again, we wonder about reducibility. All right. So now what I'm going to do is to, so this guy lives in G-dual. So I'm going to look at something which is above, so in the cotangent bundle to the flag variety, which maps under the moment map onto VLW, and say something about this. That's the characteristic variety. And so I'm going to be even sloppier about it, but then I really care about VLW, so that's why. Okay. All right, so let me write this again. So we have VLW in G-dual, okay? So now here, X was my flag variety, so I can look at the cotangent bundle. Since GX and X have a moment map. Okay. Now here, I have something which is called the characteristic variety. It is defined somehow in the same way, but you have to move to D modules. So the idea is that you have your LW, you look at the image of LW under the Bell-Invariant localization functor, you get a D module, and again, you have a notion of good filtration. And now, if you look at the associated gradient of this guy with respect to this good filtration, it turns out it is a sheaf of OT star X modules, and so you can look at the support. And this is the characteristic variety. So well, the point is that if you look at its image and nu, as I was saying, you recover VLW. Okay. So, and moreover, this is, let's say, in general, whenever you have a Whitney stratified variety and you play this game, it's going to be contained in the union. These are the conormal bundles to Schubert cells. And next. Okay. Well, now we look just at the support. So in principle, we have a variety, but what you can care about is multiplicities along this, this conormal bundles. So you have a cycle, okay, which is called the characteristic cycle. So taking multiplicities gives you a cycle. These are two C's, even if they looks like G, so characteristic cycle. So this is just going to be, well, some of the classes of these conormal bundles. And then here you have some, of course, non-negative integers. This is not useful, this proper cycle. And now, well, of course, you have some integers, and then the natural question to ask, okay, what are they, right? So what are M, Y, W? Okay. So this is a hard question in general. Okay, so it's not what we are going to answer today. Okay. So it is a hard question. Let me say some property. So first of all, MWW is 1. Then we have some vanishing property. So MYW is 0 unless CY is contained in XW. Okay. let's see why. Oh, I'm not sure I've introduced this notation. I'm not sure. So Cy is B, Y, B, B. There's the Schubert cell. And XW is singular at Y. Okay. And then I also mention, and this is what's relevant for us, that they are singularity invariants. Okay, so singularity invariant. All right, and then the first remark is that so the characteristic variety is irreducible if and only if M YW equals 0 whenever Y is different from W. So, in fact, sometimes, actually, often it is, for example, possible to say this, but, or it is possible, well, not to say that some of these MYWs are 0, but it's very, or non-zero. So, for example, to show reducibility, but it's very hard to determine them. Okay. Well, it depends. In general, very hard. So, let me write in here conjecture, or maybe just conjecture. This is due to Kazhdan-Lusztig, 80. So it was a paper where they were realizing topologically Springer representations. And so they were looking at the characteristic varieties, and they would wonder, well, they would expect them to be reducible in type A. Okay. Okay. So, well, there are nowadays a bunch of counterexamples. Okay. So in fact, maybe I didn't read it carefully enough. My feeling is that there was no really restriction to type A in the paper. But anyway, it was very soon known almost since the beginning that in other types, there are a lot of examples of reducible characteristic varieties. So the first, if you want counterexample to this conjecture, is in 1997, and it's due to Kashiwara Saito. So here they do produce an explicit counterexample, which is some Schubert variety in the flag variety. Oh, maybe I didn't use this. So in the SL8 mod B. Okay. So if you want flag variety of complete flags inside C8 at a certain and here the idea was actually they didn't go straight to the flag variety. They first found a reducible characteristic variety looking at a quiver varieties, and then they took the singularity and then they somehow recognized it inside the flag variety. Okay, and again, I'm being sloppy exactly as before, and but when we're going to have an example, I'm going to tell you exactly what I mean by singularity. We look at some normal slice which encodes all information you need. So, well, that's also maybe I'd like to mention, well, it's a paper by Tom Braden, 2001, where he studies this phenomenon of reducibility of characteristic varieties. And for example, that's an example in which he can explain why something is reducible, but cannot compute these numbers. Okay? And so that's very general, not only in type A.
Would it be a good time to have a break shortly, Martina?
Oh, it's already, okay, sure. Yeah.
Just if you want to finish
almost,
feel free to finish the thought.
2 more lines. May I? Yeah, just, okay. And then I wanted to mention, actually it's almost perfect time to have a break. So the third result I wanted to mention is a result by Villon and Williamson, published in 2012, but actually it was something started in 2010. And it was following a question by Michel, who noticed that somehow the example we knew of some non-trivial decomposition numbers for permutations would somehow appear would be in the same instances as reducible characteristic varieties. So for example, for B2 characteristic 2, which is very peculiar, but it sort of was somehow the starting point of all this discussion. So maybe let me just write this. So there is some relation between MYW and decomposition numbers for Purley sheaves. Okay, so I would say it's a good time to have a break. Maybe
okay.
I did.
We have
I do have a slide. Break. Good. All right. So here we are. So as I said, I'm still focusing on this. Okay. So okay, maybe that's also something I should have removed. So now the conjecture I want to focus on is sort of a weaker conjecture. As I said, was stated as a question in Borow-Brzezinski, was actually stated as a conjecture in Joseph's paper. And so what the conjecture is about is the irreducibility of the associated variety. Again, in type A. Okay. So, and as I was mentioning a few minutes ago, is that what happens is that so there is in fact an equivalent condition. So VLW is irreducible if and only if MYW equals 0 for any Y in the same two-sided cell. So I write LR as W and different from W, of course. Okay. So I recall what the cell is again in some nice combinatorial position. So, and now you see that from the key result, so maybe let me write it this way. So from this fact plus the key result plus well-known counterexamples. So for example, Kashiwara-Saito. To the previous conjecture, well, we get counter to this weaker conjecture. Okay. Well, in fact, as I was mentioning, now there's plenty of counterexamples to the conjecture in the previous page, and so you get plenty of counterexamples to the weaker one. And I want to, I hope I'll get to the example at the end to convince you, or at least to give you the exercise to convince you how easy it is now. But still, of course, that's so I absolutely have to mention explicitly, not only in the 5 minutes break, this fact that in 2014, so Williamson had found already a counterexample, so showed the failure of this weaker conjecture. Let me say WC. Well, okay. Of the weaker conjecture by exhibiting an explicit actually two, an explicit counterexample. Okay. And so let me tell you what the strategy was, because we're gonna borrow the first 2 points, or somehow the initial idea. So, well, the idea was somehow pick, is what I was mentioning also before, so pick Kashiwara-Saito counterexample. Okay, and we said there was some pair YW, okay, and S8 times S8. Let me write it this way, I hope you remember. So W is the indexing for the Schubert variety, and Y is the point where XW is singular at. And then what he was looking for, want to find, or two other permutation, Y bar, W bar, in some maybe bigger, let me say SN, okay? which are such that, well, they lie in the same two-sided cells. In fact, he founded something in the same right cell. That's where we got the idea from. And then, so the singularity. So the singularity is the same as before. So finally, I can be a bit more precise. So, and such that. So what you can do, so let's look at our YW initial. So you want to, so you have your Schubert variety, you want to say something about the singularity at Y. Okay? So at this point. And so what you do is that you look at the opposite Schubert cell you intersected. Okay, so that's a slice. That's something I've learned from Jenna. I should give her as a Kazhdan-Lusztig lemma. So it's telling you everything you want about the singularity. Okay, so let me denote this by NYW. Okay, and so somehow what you want to do is that assume we are in a bigger rank guy. So I'll put some twiddle. Okay. So this is going to be n twiddle y bar w bar. Okay, and so these two now are, well, they really have the same equations. Okay, so we want them to be smoothly equivalent. So these are some affine varieties. All right. So that's what he did. Okay, in a very specific example. And so to find this, yeah. I'm just thinking whether I do have enough room. I hope so. So to find such pair, okay, so this is still the vague idea. So let's say what he did finally. So to find such pair, well, now here's where he needs a lot of work. So first of all, one needs properties of the P canonical basis or P Kazhdan-Lusztig basis. So the P analog of Kazhdan-Lusztig basis. And then he needs his result, which I mentioned in collaboration with Vilonin, result of so which, as I said, was relating these integers NYW with decomposition numbers for Purvis sheaves. And then, so he needed to do some computer calculations. That's some magma package by Hallett and Nguyen. Okay, where somehow it's really a package about two-sided cells, red cells, and so it allows you to check whether the pair somehow you restrict your attention to some pairs thanks to the previous 2 points, and then you still have to check something. Okay, so that these 2 candidates are in fact in the same cell. So he manages to find an example. So he took this pair corresponding to S8, and he found the same singularity in a flag for SL12. Okay, so of course it was not possible to just check all possible pairs, so he needed all of this. So as you can tell, so thanks to this key result, this last step, you just don't need anything anymore. So you borrow the initial idea of Giorgio, which is really the core, but then that's this sort of trick, which allows you to say, okay, as soon as I know a counterexample, or for the stronger conjecture, I get a counterexample to the weaker one. Okay, so now let me move to Kazhdan-Lusztig cells. Okay, in type A. So, so we recall the Robinson-Chancet correspondence, Knut correspondence. Okay, so you have, whenever you have a permutation, you can associate to it a pair of standard tableaus. And if you restrict this to standard tableaus of the same shape, you get a bijection. Okay? So if you haven't seen this before, you just should know that you take a permutation, you write it in a one-line notation, and then that's a bumping procedure to get QX. And QX, you can either get it as a recording tableau, or you just define it as P of X inverse. so now definition, which is again in fact a theorem by Kazhdan-Lusztig, 79. So was actually used in the theory of primitive ideals of Joseph, or if you want combinatorial proof, that's Garcia, again McLernan, 88. And so we take two permutations in Sn, and now we say that they are right equivalent, so, or they belong to the same right cell, right Kazhdan-Lusztig cell. Okay. If Py is the same as Pw, okay, so this P symbol is the same, it's a tableau. And then they are right-left equivalent, or left-right, I don't know which order I wrote it, so they're in the same two-sided cell. If the two tableaus have the same shape. Okay. And so a clear remark, so if you have never seen that, you can have a look quickly at this example. I'm not going to discuss it, but a clear remark is that as soon as you have something which is right equivalent to something else, they also lie in the same two-sided cell. And so that's why it's relevant for us. As I said, that this reducibility of associated varieties is related to two-sided cells. What we're going to provide is something which has to do with right cells. So, clear remark. How much time do I have? Still 10 minutes? 10 minutes.
Oh, yeah, 10 minutes.
No, I don't know. Maybe is it okay? Okay. So, all right. So how do you prove this key result? I hope I convinced you before that was sort of useful. So you really give an algorithm, okay? So that's, again, maybe related to what Roman was asking. So it is effective in the sense that if you do have a counterexample, if you do have a counterexample for a stronger conjecture, you get explicitly, you can construct a counterexample for the other one. So we can, go through it. I wouldn't spend much time. You might just believe me that there is an algorithm. Of course, the idea is that you have whatever two permutations you like. You can forget about geometry for like 2 minutes. And then since it is about tableaus, you take these P symbols, you compare them. If they're the same, you're done. You exit and you go for a beer. Otherwise, well, of course, they're going to have a minimal misplaced entry, which since it's minimal, turns out to live in 2 different columns. And so you look at the farthest column, and it's labeled by L, so the L column, which is at least 2. And then once you have K, which was the first misplaced entry, and you have L, you can construct 2 new permutations, which are going to be L elements of a symmetric group over N plus L minus 1 letters. So the idea is that you have a string starting with K of length L minus 1, and then you copy the pattern of these permutations. So you have the first part in common, and then the 2 patterns shifted. So in fact, this is, so the result about singularities, you can get it either by explicitly writing down the isomorphism or invoking a result by Hu Yang about what's called a pattern embedding, interval embeddings. Okay? If you're familiar with that. But, so you have an explicit algorithm which you are going to use, for example, I haven't stated what I want to state first. So once you have the algorithm, there's a theorem, okay? Well, in collaboration with Peter, which says, so 1 is the above algorithm, well, of course, terminates. And it is in at most n minus 1 steps, in at most n minus 1, maybe n minus 1 steps, okay, iterations. So this is n, so your 2 starting permutations live in Sn. And then 2 is that let y bar, w bar be the final output. Okay. Then, well, I could state it just the first, so by stating in terms of MYW, because that was for us the first thing at the beginning. But in fact, what you get, so you derive this from the fact that this NYW and Y bar, W bar are the same as normal slices. And so you have as a corollary, so that's stronger, of course. So that's why I was saying that something about singularity invariance in Schubert varieties. And so a corollary is what I was mentioning before, is that from known reducible characteristic varieties, you get reducible associated varieties. Okay, so exercise, that's what I was, so I'm going to probably just put the file then in the chat or send it to the organizers. But I expect some of you to solve the exercise. So these are the two permutations corresponding to Kashiwara's Saito singularity. So exercise is to compute this pair. Okay, so to prove that associated varieties for LW with this W is reducible. All right. So last, So last few minutes, I thought I'm just going to, that's a very baby case. So it's not about a reducible characteristic variety, it's just about these slices, so that I can give you a flavor of what's going on. So let me, so it's just a baby example of the first singularity you find in Schubert varieties. So, well, here we pick two permutations in S4. Okay, again, that's the one-line notation. So 1 goes to 2, 2 goes to 1, etc. So these are the corresponding P symbols. Okay, so constructed by bumping procedure. And now, so we start scrolling them down. So 1 is always placed in the same spot just by the algorithm of Robinson, Shenson, Knut. Then 2, and then 3, and then 4 is the first misplaced entry. Okay. So the K in the previous algorithm is 4. And then now the column we have here is in column 1, here is in column 2. So we had an L, which is 2. So maybe let me copy this. Oops, no. Maybe it's too big. Maybe we manage, let's see. Yeah, okay. So now let's see. So now I have to look for the first misplaced entry, which is 4. And then I need a string of length L-1, so 1. So it's a string which has only 4. Okay. Otherwise, if L were bigger, I would have 4, 5, 6, etc. of length L-1. And then, so here I have 4, and here I have 4. And then I copy the patterns. Okay, so here I have 2, 1, 4, 3. So 2, 1, now 4 cannot appear again, so it becomes 5, and then 3. Okay, and here's the same. So 4 cannot appear, 5, and then 2, 3, 1 are the same. And so you can make this precise with a formula. Okay, so we had them. And then at this point, that's a baby example, so it's a bit boring. The algorithm terminates already because you construct the tableaus. You construct the tableaus and you get the same guy, okay? And now let's look at the normal slices. So normal slices, type A Schubert varieties are pretty in the sense that you have, as always in type A linear algebraic description, a very explicit description. And so you can realize NYW this way, okay? So maybe, so if you've seen this already, great, you can recognize what's going on. If not, trust me, because I would have only 4 minutes, there's no way. Maybe just, so you see here you have 1, 1, 1, 1, and these are given by the positions of Y, okay? So this is the matrix, permutation matrix corresponding to Y, because you're looking at something around a singular point, okay? And so here you have these 4 parameters, and that's the equation they have to satisfy. This appears by intersecting with the Schubert cell corresponding to W. And so you have a cone, right, singular. Here there's this other guy. So, and well, I could have, well, just written here 0. That's the reason why I put 0 here, whatever. And as you see, it's really the same equation. Okay. So it's, you have this, or maybe you have the same singularity. Okay, so that's really what you want. And so since, again, in general, you might wonder whether you have interest in singularity invariants lying in the same right cell, you say, well, yes, they're exactly the same, I mean, as everywhere. So there's nothing special about lying in the same right or left or two-sided cell. Okay, so that's nothing different from the rest. Okay, thank you very much. You're right, grazie.
Thank you. Thank you very much. Are there any questions? Aha, so can you see the chat, Martina?
Let me, yeah, maybe I can. I think, oh wow, let me understand which one is the last one here.
I can read it out.
This is, oh yeah, a question of Williamson's result. That's the last one? Yeah.
Yes, yeah. Or I can, yeah. Yes. No, I mean, you have, it's not, yeah, it's not exactly the same. So you have some, so what you do is the following. Let me try to explain. So the question is, so you have, if you want 3 things, so you have decomposition numbers, you have these MYWs, and you have, so you have a KL basis and PKL basis, and then the basal change coefficients between the 2 variants of canonical basis. Okay, so the question, I think, as far as I understand, is what's the relation between the coefficients appearing to move from the Kazhdan-Lusztig basis to the p-canonical, or vice versa, from the p-canonical basis, p-Kazhdan-Lusztig basis to the Kazhdan-Lusztig basis, and the composition numbers, right?
Yes, yes.
Yeah, okay. So, so what happens is that what you can do is to look at the first non-trivial, first non-trivial decomposition number. Doesn't sound clear, maybe yes. Yes, I think that's the way you want to say it. So you have you have how do you say this? So yeah, as soon as you, so let's say you take your IC guy, so you first look with integer coefficients, and now you base change it, and now you want to see if it decomposes as a IC over, as a Purley sheaf over FP or in characteristic P. Okay, so now again, you're going, of course, by the support condition, you might get terms which are coming only for elements which are less or equal than the one which is indexing in the guy, the IC guy over Z. And now the first instance in which you find some non-trivial decomposition number, well, you're also going to find that the p-canonical basis has some non-trivial coefficient in front of, so it's also not going to coincide with the Kazhdan-Lusztig base. I don't know, maybe Carl, you can explain this better than me. I don't know. Just because I see your face, there are probably plenty of people. So that's a list. Okay, I'm indulging in being optimistic.
Sorry. So the question was whether there is some, well, whether this story gives some control over the set of Y and W for which W is not zero.
I mean, these I doubt, because these are very specific guys. So as far as I can tell, so I was cheating a little bit. So George's counterexample is a bit different. That's why I know that it is too optimistic, Roman, because he really gets, so he starts with Kashua site, and the trick is the same. So the idea of embedding the singularity. But then he gets a different pair of permutations. So that's not the pair you will get with the exercise.
So there are cases when MYW is non-zero and YW in the same cell, but they do not come by this procedure that you described.
No, you can't, because in fact you can do similar things like put in the sequence at the end. So you have way more symmetries. I mean, this was just to produce one, but you can do. So for example, right? You know that if you look at Schubert variety XY and you look at the singularity XW, and you look at the singularity of Y, and then you look at inverses. So XW inverse and the singularity of Y inverse. Well, the singularity is the same, but it's not something you're going to see here. So I mean, you don't get that pair, for example. But then you know that also before you have that counterexample. So yeah, I don't know. I doubt that you get all of them, just because I'm pretty sure that, yeah, you have way more examples already for flags in C12 than the ones we would get. I mean, that's my feeling. Because I think before S8, you don't find anything. And maybe I'm wrong. I doubt, just because, I mean, some of the examples Georgie gets by computer calculations, you don't really get them that way.
Thanks.
No, that would be great. That would be, yeah.
I guess, are there any other maybe quite brief questions? Because we're just coming up to the hour. Okay, Anton has a question. Is the Brouwer interval for the new pair of permutations isomorphic to the old one as opposed to?
Yeah. This is, I mean, either you can prove it in three ways. So either you write down, so in a previous version of the paper, you just write down explicitly the isomorphism between the Richardson varieties, okay, and then you see that it is T equivariant. So T is the maximal torus on the small Sn, and the bigger torus factors through the action of the smaller one. So that's one way. A second way is you invoke Ehresmann criterion. You just look at tableaus. And so you have one, like these two permutations written, the four permutation written in one line notation, so you check that you get exactly the same, by induction, you get exactly the same interval. And the third one is, again, invoking this paper by Hu Yang, who proved that if you have this property of interval embedding, that you get an isomorphism of Brouwer intervals.
Okay. Well, let's thank the speaker again, in whatever way we do online, and we'll continue in a minute.